I've expanded on what I've figured out over the last couple of years, but this week is still a largely superficial overview of Bayesian statistics. This semester is focused almost exclusively on null hypothesis significance testing using parametric approaches. This is the classical frequentist paradigm, which is based on the computation of the probability of an event. Rather than derive a distribution of event outcomes using an arbitrarily large number of experiments, we instead assume a set of parameters that describe a function that produces a distribution of event outcomes. The probability of an event is the number of times that event occurs divided by the number of possible outcomes. In the long run, as the number of tests approaches infinity, the relative frequency of the event of interest should approach its true frequency in the population. Here's the thing about those p-values. They are predicated on an assumption that you will collect your study data and analyze it exactly once at the end of collection. No ifs, ands, or buts. However, that's not always how it goes. Suppose you used a power analysis to run a study. It said 60 people would be sufficient for a study with a power of 0.9, which is reasonably high. So you collect data from 60 participants, run the ANOVA, and your one-way ANOVA falls just shy of significance with a p of 0.07. Now, if you try to write up a study as is, you'll have a hard time publishing a study with a marginal effect. You could abandon the study altogether, but there goes a year of your life. 0.07 is awfully close to the 0.05, and it certainly looks like something might be there. Maybe if you just ran a few more participants. Well, this is an option that many people would take, since it makes the best use of scarce resources. However, when p is greater than 0.05, it means retain the null, not try a little bit harder. The figure on the right plots the effective type 1 error under the null hypothesis after each test. On the far left, when you check only once, when the nominal alpha is 0.05, the effective type 1 error rate is also 0.05. However, if the null hypothesis is actually true, and we choose to keep on collecting data and checking each time, the extra kicks at the can inflate the effective type 1 error. If we were really persistent and willing to add up to 1,000 extra participants, rerunning the ANOVA each time, we would have an approximately 50% chance of incorrectly rejecting the null and making a type 1 error, though we would have reported a type 1 error rate of 5%. The significance test does not mix well with adding new information, because under the standard testing procedure, adding new information makes the resulting statistics less accurate. The problem with the null hypothesis significance test is how the question is formulated. You are making a binary determination against the default assumption that nothing is going on. And we test the same assumption over and over, which is kind of strange given that previous experiments may have told us that something might be going on, but it appears to be a hit or miss for reasons that we'd like to pin down, or that something definitely is going on, but we just don't know by how much. So even though the alternative hypothesis may change over time, the null hypothesis never does. This may not sit well for those who appreciate balance. The Bayesian approach turns the hypothesis test paradigm on its head. These methods integrate background or prior information into the statistical model. The approach is still rooted in probability, but it still expresses the outcome as a degree of certainty, somewhat like a confidence interval. The Bayesian model combines any background information with new updated information from the present data to revise our model. In a way, this approach is built for peaking, because adding new information to the existing information makes the model more accurate rather than less accurate. Here is a table of similarities and differences between the standard hypothesis testing approach we've been using all year and the Bayesian approach. I won't narrate the table to you, but you can review the table in the lecture notes. The two approaches are most similar with respect to how confidence intervals and credibility intervals are interpreted, but in many other ways they are polar opposites. If you recall, we use our inferential statistics to infer what the true value is in the population, based on the values we observed in our sample. Thus, a core assumption of the approach we've been using is that there is one true value that we are trying to guess at. It's kind of like entering one of those raffles where you have to guess the number of marbles of a particular color in a jar based on what you can see after shaking the jar up a little bit. And also, the prize is a job where you get to come up with other clever raffles to play. Now, the Bayesian approach does away with trying to play a guessing game altogether. Instead, it determines a distribution of likely values. Bayes' theorem, shown on the right, is a computation of conditional probability. This actually comports better with how we often compute probability, because many of our decisions are informed by prior information. If you park in a no parking zone while you run in to pick up a pizza order, what is the probability that you'll get a ticket? Whatever your estimate is, it would probably differ given the additional information that there is or is not a parking enforcement officer in the area. The Bayesian approach calculates the probability of some event, for example that two means are different, given the information at hand. The information at hand is a combination of some newly collected data and possibly data from the previous experiment or assumptions, which are called priors. So what constitutes prior information? Prior information consists of any relevant information we have about the population parameters prior to our experiment, and we will use our experiment to modify our beliefs about these parameters. These beliefs may come from earlier studies, for example showing that a treatment lowers the score by some amount relative to the controls. These beliefs may also capture uncertainty in the data, for example with contradictory results from studies showing a treatment may either raise or lower scores by some amount relative to controls. To show how priors might differ in informativeness, let's consider an example where we wish to estimate the population mean and variance of reading skill in children on their very first day of school. The relevant characteristic here of our prior knowledge is called precision, which reflects our degree of certainty about the distribution around our prior belief of the population mean. The more certain we are of the mean, the smaller the variance of the prior distribution. As we add information, our certainty should increase. Consider the following prior distributions. In the top left, we have prior 1, a non-informative prior. In this case, we make no particular assumption about what the true population might be, nor what values might be more or less likely. Any possible score between plus and minus infinity is assumed to be equally likely. Prior 2 is only slightly more informative. We're still not any more specific than allowing that a score will be some value between plus and minus infinity, but at least we are allowing that some scores will be more likely than others. If we incorporate what we know about test scoring, our prior knowledge can be even more informative. For example, suppose we know that the lowest possible score on the reading test is 40, and the maximum possible score is 180, but don't have information about the likely distribution of values within that range, as in prior 3. With that additional information, our prior beliefs of the population mean need not consider values extending out to infinity. Just ruling out those impossible values is a huge increase in the informativeness of what the true population mean might be. However, additional information might make us more certain about what the population mean is likely to be within this range. Suppose, for example, we know that the test is standardized to have a population mean of 100. Then we might believe that the population mean is more likely to be close to 100 than to either extreme. This would be reflected by prior 4. Additional information about the standard deviation of the standardized test might lead us to be more certain that the mean score will fall within a narrower range, as in prior 5. Finally, suppose we gain additional information about the population that might lead us to anticipate a lower score. For example, children from low SES households are less likely to be highly skilled readers before starting school, because their parents are less likely to have time to regularly read with them, and so we shift our distribution downwards. So priors allow us to apply any relevant information we might already have about the parameters of interest before starting our experiment. The informativeness of this information falls on a continuum, from completely uninformative to very informative. Despite what my vignette suggests, uninformative priors don't mean you're working with doofuses. It just means that you're starting off with no expectations about the parameters. Very informative priors, in contrast, give you very specific expectations about those parameters. If you don't want to specify priors, either for lack of information or because you believe the prior information to be irrelevant or inappropriate for some reason, you can use non-informative priors, also called objective priors, which won't influence your final probability estimate. If your prior expectation is only that the population parameter is some number between plus and minus infinity, well, the probability of that is going to be 100%. So, when you use Bayes' theorem to compute the posterior probability for your new data, you're just multiplying by 1. If objective priors contain no information, then as you include more prior information in your priors, they become more subjective. Subjective priors can be beneficial because they incorporate previous findings. This will generate more precise probability distributions, which are similar to confidence intervals that use smaller standard errors. So we always need to provide a prior distribution for all the parameters in the model, but we can choose to provide uninformative priors if we have no relevant information. The model parameters include both the population mean and variance, and so priors must be provided separately for each. However, these priors are independent, and so we can use a highly informative prior for one and an uninformative prior for the variance. For example, we know that at the very minimum, the population variance is going to be a non-negative number. Now that we've established what we know going into the experiment, we can add our obtained evidence to our model. After we've specified our prior distributions for all the parameters in our model, we add our newly collected information. Our prior beliefs about the range of likely values for our standardized test of reading skill give us some expectations about what our population mean and variance is likely to be. Now we have obtained the reading scores of 20 children on their first day of school. Our data are summarized by a likelihood function that describes our parameters of interest. In this case, the population mean and variance for the reading test scores, given our dataset. The likelihood function is similar to the probability distribution of the sampling mean. It is a function that computes the probability that the population parameter falls within a given range, given our evidence at hand. So at this point, we have our prior distribution, and we have a distribution based on our evidence at hand. Our posterior distribution will reconcile these two distributions to update our beliefs about the model parameters. A posterior probability interval, or PPI, mathematically reconciles the probability distributions generated from our priors and our new data. If our new information overlaps with our priors, this confirmatory evidence makes us more confident about those values for which the two distributions overlap. However, it is likely that there will be values for which our priors and our new data are inconsistent. By the same logic, we are less confident about those values where our priors and our new data are inconsistent. So, a PPI is a probability distribution that reflects our updated estimates of the probability of a parameter taking on a certain value. It's kind of like a cross between a confidence interval and one of those parametric distributions we're familiar with, like the standard normal distribution. So you might report a 95% PPI, which would be the segment of the probability distribution on either side of the most likely value and covers 95% of the area under that distribution. The posterior probability function is computed by multiplying them together to produce a composite function. You can see the results of combining different priors with the same observed data to generate different posterior probability intervals. When the prior is uninformative, all values are equiprobable, so you're multiplying the observed probability estimate by 1. The resulting PPI overlaps perfectly with the estimate from the observed data. When we have low information priors, the reconciliation of the two probability distributions produces a posterior distribution that is largely biased by the new observations, but we are more confident about the values where the priors agree with the new data. So we see the PPI has a higher peak where the priors also predicted the most likely values. When the priors are more precise, we are saying we have a very good reason to believe that the probability function for the population parameter has a particular shape and falls within a particular range. You would use prior 4 to indicate that the values could fall anywhere from 40 to 180, but that you believe 100 is the most likely value. Prior 5 is even more specific, indicating that although the test scores could range between 40 and 180, you think the population mean most likely falls between 90 and 110, but again 100 is the most likely value. There will be regions in which the prior and observed distributions mismatch and where they overlap. The PPI will reflect a compromise between those distributions.